This is my lecture on Lab 3, Spectroscopy and Analysis with Light. This is a virtual lab. Experimental data will be given to you, and you will write the lab report as if you had done all the experiments and collected those data. There are 3 parts. Part 1, energy of light. In this part, you will collect the voltage that excites an electron from a lower energy level to a higher energy level. And then this electron may jump back to the original lower energy level and emit a photon. We will be able to collect the wavelengths of the photon and the corresponding voltage. Now, under 1 volt potential, electric potential, an electron may get 1 electron volt energy. 1 electron volt energy is equal to 1.6 times 10 to the power of negative 19 joule. So this is the theoretical part. Now let's look at the apparatus. Right here, you have a DVM. You see the voltage here. And this is the energy of light apparatus. We can adjust the voltage by turning this knob. We can select one of the 7 LED light bulbs, each with a different wavelength. So you can see those numbers, 470, 502. Those are the wavelengths of the photons. 470, that's blue light. 640 is red light. Visible light is between 400 and 750. So these two are 880 and 940. You will not be able to see these 2 lights. You will have to use a camera phone to convert UV light to visible light. I want to show you the wavelength more clearly. 470, this is blue light. 640, this is red light. 568, I think it's yellow light, but you can just Google the visible light spectrum to see which wavelength corresponds to which color. 880, 940, again, they are infrared. They are invisible to human eyes, but I think snakes can see infrared light at these 2 wavelengths. The unit of the wavelength here is nanometers. All right, 7 of them. Now again, what you need to do is you need to adjust the voltage so that you can barely see the light. Right here, I think I'm looking at orange light. All right, so this is orange light with wavelength of 602 nanometers. This is orange light. Now I'm going to give you the data. Those are the experimental data. We have the wavelength, we have the voltage. And now you need to use Excel or OpenOffice. Maybe I should put it here. Whatever software you use. Or you can use Google Spreadsheet. You need to convert nanometers of the photon to hertz of the photon. Nanometer is the unit of wavelength. Hertz is the unit of frequency. And also you need to convert the voltage to energy. So 1 volt is equivalent to 1.6 times 10 to the power of negative 19 joule. This is because the charge of an electron is 1.6 times 10 to the power of negative 19 coulomb. So if you increase the potential of one electron by 1 volt, you increase its energy by 1.6 times 10 to the power of negative 19 joule. And once you convert this column of wavelengths to frequency and this column of voltage to energy, you will be able to plot a energy versus frequency graph. I think you have learned the Planck constant. The energy of a photon is equal to the Planck constant times the frequency of the photon. So there's a linear relationship between energy and frequency. The slope is supposed to be the Planck constant. So by choosing this data and plot the Excel graph of energy versus frequency, I think you will be able to get a slope fairly close to the Planck constant. Be sure to set the intercept to be 0 because the equation is this: energy is equal to Planck constant times frequency plus what? Plus 0. Your number is not going to be exactly same as the well-accepted value of the Planck constant. It's going to be different. So you'll calculate the percent error. The percent error is your value minus this value divided by this value. And then you multiply that number by 100%. The percent error can be positive or negative. If your result is smaller than the well-accepted value or true value, you'll have a negative percent error. And that's fine. Now I'm going to show you how to do this data analysis. This is my Excel spreadsheet over here. I have 2 columns, wavelengths and voltage. All right. And what I will do is I will show you how to convert the wavelengths to frequency. First, this is in nanometers. Well, I just convert this to meters first. If you look at this equation, I'm multiplying the wavelengths in nanometers with 1 times 10 to the power of negative 9. So you can put this 0.0000000001 here, or you can make your life easier. Just enter 1e minus 9. That will do. All right, and then over here, I'm going to just click this filled square on the bottom, and I drag it down. All right, so I got this wavelength in meters. And from wavelengths to frequencies, how do we do this? Well, it's very simple. The speed of light is equal to lambda times frequency. So frequency is speed of light over lambda. Let's click this cell. Speed of light over lambda. Well, you can put 8 zeros here. After 3, you can say 3e8. That's also the speed of light. 3 times 10 to the power of 8. And then, again, you can click this very small filled square. Click here and drag it down. You generate all the numbers. Now, energy. Energy is simply the voltage times 1.6 times 10 to the power of negative 19. Right here. So again, you just drag it down. And we have all the data. All right, now we have all the data. And then how do we create this graph? Well, select this 2 columns and insert, scattered. Over here, you get the graph already. So this data points are the same as this data points. Well, but if you compare this to over here, I had the title, axis labels. The numbers are formatted. The font size are bigger. I got an equation here. So we can quickly change all this. Okay, I'm going to use font size 16. All right. And I'm going to use bold font. And I'm going to use black. It was gray. So now it's black. And you can just right click here and change the format of these numbers, I believe. Over here, let's look at number. We'll use scientific number. We don't have to have any decimal places for the axis. Alright, you can change the minimum, maximum. I think over here I'm going to just use maybe 1 times 10 to the power of negative 19. Alright, so that's how you change the axis. And then you add the axis titles. You probably think of a name here. I'll let you type it up. My graph is energy versus frequency. You can say determining the Planck constant. And also we need, I think, the trend line, right? We need the trend line. Or do a linear regression, or do more options. We will set the intercept to be 0. Alright, on the bottom here, display equation on the chart, display R-squared values. Alright, and then right click here, we can format the label. So I'm going to format the label. Let's see. The number, maybe we'll do scientific, okay, or do scientific, okay. And you can specify the number of decimal places as well, all right. And then you change the axis title to energy in joule. The horizontal axis is frequency in hertz, and of course you need to change the title, and then you get the same graph here. The slope is 6.09 times 10 to the power of negative 34. This is slightly smaller than the Planck constant, but that's normal. This experiment is not 100% accurate. All right? And also, you probably can see whenever I do something to, for example, I just hit enter, the number changes because I generated this voltages a bit randomly. So I want to show you my little secret here. I'm using a random function here. So this 0.06 times this random function will give me a number between 0 and 0.06. So really this will give me a number between 0.97 and 1.03. So I'm creating a random reading, voltage reading here for you. All right. So as you can see, these numbers may be slightly different from the numbers in my lecture notes. Just use the numbers in my lecture notes. Okay. So just use these numbers. All right. Type up these numbers in your Excel or OpenOffice spreadsheet. Convert nanometers to hertz. Convert voltages to joule, and then do a linear regression and get the slope. Don't forget to set the intercept to 0. All right. So this is part 1. Part 2. Part 2, I'd like you to watch a video on the flame test. The video is here. I think I can show you the video here. All right. So it's only a 2-minute video. Okay. So you're looking at the flame of a potassium compound. The color is lavender or violet. You record the color and look up its corresponding wavelengths. Okay, you can simply estimate the wavelengths of a violet photon. I'd say maybe 400, 420, 430. So it's just your estimate. Now I'm going to give you the experimental data. Really, it's observation of different flames. You can see there are 10 compounds here. They have different colors. All right. This is how we make fireworks. 3 more compounds, 3 different colors. And then this is strontium nitrate. This should be lower subscript. Copper sulfate. This is boric acid. This sodium nitrate. So anyway, you can see the colors here, and guess the wavelengths, and fill in the tables or blanks, and then answer some of the questions. Now, part 3, atomic spectra. So we'll have to observe some spectral lines of some so-called gas discharge tubes. Here are a few examples. Helium, neon, argon, kryptons. So if you look at this light bulb, inside you have neon gas, and electricity may excite the electrons in the neon atom. And they jump to a higher energy level, but eventually they have to jump back. When electrons jump from the higher energy level back to the lower energy level, a photon is released. In this case, you can imagine we'll see red photons being emitted. But actually, there are photons of other colors. It's just this red color is predominant color. All right, and also you observe incandescent bulbs and fluorescent bulbs. Okay, those are the observations. All right, and over here 4 to 7 are 400 nanometers to 700 nanometers. This incandescent light bulb will give you a band of colors like a rainbow. But if you're looking at atomic gas tubes, like hydrogen gas tubes, well, sometimes it's labeled hydrogen tube, but really it's hydrogen atom. You will see only 4 lines in the visible range. Okay, they are marked with the corresponding wavelength: helium, mercury, and neon. And now you have enough data, or actually enough observations of spectral lines to finish part A. In part B, I want you to identify this gas. I'm not going to give you the spectrum. I'm giving you 4 numbers. Given the 4 numbers, you should be able to guess what this element is, based on your observation of part A, part 3A. And then you can finish the lab report for this virtual lab.